So far, with the goal of learning the different rules for differentiation, we've talked about rules such as the power rule for differentiating functions such as this. If I have a division by x cubed or the square root, I can change those to power functions and apply the power rule, where I could drop the power and subtract 1 from the exponent to find the derivative. More recently, in live class, we talked about, well, what if I have a product of two different functions? Of course, I could multiply those out and then do the derivative after, but we can always apply the product rule, which if we call this function f and this function g, would be first d second plus second d first, or f g prime plus g f prime. And similarly, the quotient rule applies towards solving derivatives of fractions or of division of two functions, like if we call the top f and g. In this case, we are not able to actually divide these functions, so we would get stuck if we didn't have the rule. Again, if we call the top f and the bottom g, it's always low d high minus high d low, and that's all divided by the bottom squared, or low d high minus high d low, square the bottom, and away you go. So, or in this case, you could say it as g times f prime minus f times g prime, all of that divided by g squared. So the main thing I wanted to get at this video is a new rule called the chain rule. And this rule can seem a little bit similar, or it can be easy to mix up with the power rule, or I'm sorry, not the power rule, the product rule. But I wanted to first start by talking about when is the chain rule needed and how is it different from these other rules that we've covered so far. But looking at a few examples, if we see, what if we were curious about the derivative of the square root of a larger polynomial? As we know, for the derivative of the square root of x, we can change it to x to the 1/2 power and use the power rule from there. However, what if there's more than just x within the square root? This changes the derivative and it becomes more complicated. And the chain rule is very vital in understanding how to approach this. Or what if, for example, I had a polynomial to the 5th power, meaning there's lots and lots of multiplication here. Again, the idea behind the chain rule is we always use it when we have a function within another function. Or sometimes I call it function inception. It's like a function within a function. That's always how you know when the chain rule needs to apply. Or here I can kind of imagine I have this larger polynomial and the whole thing is raised to the 5th power. Or here the whole thing is raised to the 1/2 power. Or here the whole thing is raised to the 4th power. In all of these such cases, we would need to use a chain rule. And we can't use the product rule, especially in an example like this, because there is no multiplication of two things. So to review I wanted to review a concept called function composition, because that's these are really the same ideas when you have something within something else. And in math, we often write this as f circle g, or as we'd say f composed with g, the composition of the functions f and g. And this is a different function operator than multiplication. Remember that this small little dot means multiply, but an open circle means something else. It means composition in the context of mathematical functions. Or another way it's commonly written is f of g of x, and that's kind of what the O, you can remember, represents of. Which just means you're taking a function of another function, which is noticeably different than f times g. This is f of g. So let's do a few examples. Let's say we let f of x be x cubed and g of x be this rational function, x squared plus 1 divided by 5x minus 4. And it asks us to find f circle g, g circle f, and then we'll explore what happens when we take the derivative. So, and another thing is function compositions, you always need to use a chain rule in these cases. There's sometimes ways around it, but that's it's important to understanding the chain rule, in my opinion. But basically, f circle g, again, I could rewrite this as f of g of x. And my tablet is misbehaving right now, so I'm going to be doing this with my mouse. Hopefully it is legible enough. Which, again, how I recommend figuring out what f of g of x is by, I like to substitute g into f, because that's literally what it means. Is I want to take f of, I'm changing the input of f to the entire g function. So basically, I'm just going to copy my g function inside the parentheses of f of x. And again, what this would mean, kind of like f of x plus h, would mean plug this whole thing into x in the function. Now, in this case, f of x was relatively straightforward. It's x cubed. So what I need to do is I need to take the inputs and replace that inside f of x. So basically this whole thing will be cubed, that is, because that is what f of x does. It cubes my input. So basically f of all of that would just be all of that to the third power. And technically I could multiply this all out because the third power just means 3 of them multiplied together. And then it would be a bunch of multiplication, and then I could use the quotient rule to find the derivative of this if I wanted to, but that is is very tedious. Another thing about function composition is it is not commutative, meaning that if I was to do it in the reverse order, it's actually going to give me a different function. So if we were to look at, well, what is g of f of x? This is actually going to be a different function. And another thing is sometimes we call function composition function chains. It's like a chain because they're chained together. And that's where the chain rule comes from in its name. So if we were to do g of f of x, well, f of x is just x cubed. It's not so bad. And the difference here would be instead of plugging g into f, I'm plugging f into g. So what I'm just kind of imagining is, well, f of x is x cubed. X cubed is just going to be placed into g of x. So let me go ahead and underline with g of x. G of x means, well, I'd take this number and replace it here and here. Or again, if it's an algebraic expression, it works in the same exact way. So if I'm plugging x cubed in, basically all of those x's are just going to change to x cubed. So I would have x cubed squared, which would be x to the 6 plus 1 divided by 5x cubed minus 4. So I'm substituting those both into x cubed. And remember, when if you square a cube, those are multiplicative, which is why it turns into the 6th power. And anyways, these are actually notably different. Notice if I was to actually cube all of this, it would be quite a bit longer and more difficult of a function. So the next question, and the whole point of the chain rule, is to figure out, well, what is the derivative of these chains? Like, say I want to know what's the derivative of this, or what's the derivative of this. How would I approach that? Well, like if we're looking at g of f of x, this is just a rational function. It was easy to simplify. I can find the derivative just by the quotient rule here. But this one, I would actually need to fully algebraically expand it first. Chain rule is a much easier approach at that. But let's just kind of compare the derivatives to f and g, and then what happens if we take the derivative of a chain, because it's important to note that it's never as simple as just taking the derivative of each of them separately. It's kind of like how with the product rule and the quotient rule, there's a little bit more to it than just like with the sum and difference rule. With the sum rule, if we have the sum of two functions, we can just take the derivatives of them separately. It works. But with products, with quotients, and with chains, it does not work so easily. But let's just check it out. So if we're looking at, well, what is f prime of x? That's just x cubed, so the derivative, we could apply the power rule and we would get 3x squared. Now with g is a little bit more complicated, but we could use the quotient rule to do that. So for g prime, it would be low d high, which would just be 2x, minus high d low, which would just be 5, square the bottom, and away we go. Would just be 5x minus 4 quantity squared. And if I was to simplify this a little bit, move this over here, that would leave me with 10x squared minus 5x squared, which would be 5x squared. Then I would have minus 8x, and then minus 5. And remember to be careful with your distributive property and with your negatives with the quotient rule. Very easy to mess that up. And the denominator would just be, I'll go ahead and just leave it as factored for now. The 5x minus 4 squared would be 5x squared minus 40x plus 16. Anyways, so the question is, well, what is the derivative of the composition of these two functions? Is it a simple combination of the two? And again, we could look at this by, well, we know what the composition g circle f is. So if I want to know the derivative, I could just do, well, what is d dx? Oops. I'm trying to do this with my mouse. But what is d dx of g circle f? So I'll go ahead and copy it down. And, you know, since this one simplified quite nicely, I could just use the quotient rule once again. Oops, this should be -4. And again, I could get, well, low d high would be 5x cubed minus 4 times 6x to the 5th minus high d low. High is x squared, or x to the 6 plus 1. D low would be 15x squared. And then I would need to square the bottom. And away we go. And again, we could continue simplify, but at this point, the point I'm trying to make is quite clear. And I forgot my square. This has really nothing to do with f prime and g prime individually. If you're thinking about, well, how could I combine these two together to get to this? It's not just some sort of multiplicative or algebraic simple combination of the two. The chain, and that's this again. This is where the chain rule comes into play. And connecting the dots between f prime and g prime and the composition of those functions. And, again, looking at if I wanted to do f circle g and wanted to know what's the derivative of this, again, the only way we would have to approach it is to actually expand and do a bunch of algebra. And again, the algebras, a lot of times you can do it. It's just more tedious. The chain rule is much simpler. In the next video, we will talk about this more and actually get into the rule itself.